Okay, so can Joy smell Parkinson's, guys?
Yeah.
Yeah. What was it that convinced you?
She got 12 out of 12.
She got 12 out of 12?
And she predicted it before the doctors could catch up.
Or even like that 12th out of 12 actually happened where she figured out, she said, hey, they have Parkinson's. And then the doctors were like, ha, 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 no. And then what happened to that person? They developed Parkinson's, so she's smarter than the doctors at this point in terms of diagnosing Parkinson's anyway. Okay? And so we kind of, when we made our, dot plot of guesses, right, this dot plot that we did, we were just guessing. So we pretended that null hypothesis was true, right? So, and then we said, if our sample is unlikely when the null hypothesis is true, that's evidence against it. If what actually happened isn't supposed to happen, then that underlying assumption of that null hypothesis is a crappy assumption. Okay, so this is a different kind of statistical inference. We're going to learn about two different types. The first one is a confidence interval where we are making an estimate. This one's called a significance test. And in a significance test, we're just trying to decide against a claim or for a claim. But we don't really decide for a claim. But we try to decide, is a claim incorrect or not? We're testing a claim. Okay. All right. So the basic structure in terms of how you set things up is going to be very, very similar. You don't have to use the boxes. You never have to. But, man, I sure would if I were you guys so I don't forget anything. Okay? And the only big difference is, in this one we put our calculations. And in this one we put our conclusion. In this one we're still going to do the procedure and the conditions. The only difference is we're also going to add the hypotheses. All right. Now, let's first start with how do I write my hypotheses. The name of the procedure we're going to be working on right now is going to be a one sample Z test for P. Notice that that's very, very similar to a one sample Z interval for P. And it really just depends. Test you do for a claim. Interval you do to make an estimate. Okay? All right. So that means your hypotheses, if you're doing a one sample Z test for P, are going to be about P. They're going to be about that unknown parameter. Your null hypothesis is going to be of the form P equals something. I'm going to use a question mark. Okay? And that something is always going to be the claim. Now, we decided that Joy could smell Parkinson's because we rejected that she was just guessing, okay? Your null hypothesis will be what you hope to reject. Is this okay? All right. Your alternative hypothesis could take three different forms. It's always different from the null hypothesis. So, it could be, like with Joy, P is greater than whatever that claim is. She's not just guessing, she's doing better than just guessing. Okay? Or it could be a less than. There's one other thing it could be. Does anyone want to guess? Well, it can't be equal to my null hypothesis.
Oh, yeah.
It's equal to.
Not equal.
Yeah.
Not equal.
It's not equal to. Okay? And it just depends what we want to be able to conclude at the end. And hopefully that'll become clear. Now, in terms of Joy, hers was greater than. But couldn't we have done the exact same thing with Joy and said, let P equal the true percentage of times she was wrong? And if she wasn't just guessing, she would get less than 50% wrong. It would have been the exact same thing, yeah? All right. Now, we have these sets of hypotheses have, we call them either one-sided or two-sided. Both of these ones are one-sided. Think of it as greater than is one side, less than is one side. And then when you have P is not equal to means greater than or less than. Do you guys get, so that would be two-sided. Okay? I doubt we'll get to why we care about that today. We might get to why we care about that today. We'll definitely get there on Monday. All right. You guys, the assumptions. Do those look familiar? They are practically, not quite, the exact same thing. Okay? And when I say they're the same assumptions, how you check them is going to have the tiniest bit of subtlety to it. Is this okay? And before we talk about that, I want to talk through what we know about the distribution of p-hats. Is everybody okay? What do we know about the mean of the p-hats?
It's 0.
The mean of the z-scores is 0, but the mean of the p-hats is p. Now, remember when we did this, to calculate the probability that we're going to be using, right? Okay? We assumed the null hypothesis is true. So when we're running a test, what can we say about the mean of the p-hats when we're running the test? The mean will be p, but it's not just p, it's the p of the null hypothesis. We usually call that p0 or p null, p with a subscript 0, just like the null hypothesis has a subscript 0. Okay? And the standard deviation of these p-hats will be p0, 1 minus p0 over n. Does this feel comfortable? All right. So, you guys, let's talk about the random condition. How do you think we're going to check for that? How have we checked the random condition so far? We're just going to look and note that this sample is random. Okay, normal? The general rule of thumb for this graph, under which situations will this graph be normal?
I am here.
When are the p-hats normal, y'all?
The P is the null. It's equal to null. The null one.
Say that again?
Like the P is equal to the null. Hypothesis, like probability.
Well, that would suggest that the null hypothesis is true, yeah. But in general, what's the general rule for p-hats to be normal?
Greater than, isn't the n times p hat is greater than or equal to 10 n times n?
Okay. You're getting, sort of, but no. Okay? The general rule for the p-hats to be normal is np and 1 minus p. Both have to be greater than or equal to 10. And when we were doing the intervals, we have no value for p. So we had to use p hat. Cool? Do I have a hypothesized value for p when I'm running the test? I sure do. I'm assuming that that null hypothesis is true. Okay, so it's still going to be a version of np and n1 minus p. When we have no hypothesized value for p, we use p hat. In this case, our hypothesized value for p, we do this whole thing assuming that that null hypothesis is true. Okay, so the normal condition will be np null and 1 minus p null has to be greater than or equal to 10. So the same like skeleton, but the guts of it is a little bit different. But the logic process is when I have a hypothesized value for p, I use it. If I don't have one, I'm trying to estimate it, then I have to use p hat. Is this okay? All right. And then independence, it's going to be the same. N has to be less than 10% of the population. All right, so let's kind of go through one of these. I'll let you guys read this for a second. I read it last period. Okay. So the setting up of the test, when I say how would you set up your test, guys, setting up a test is just that first box. Okay, so the very, very first thing we would do is write some hypotheses. Okay? Does anybody want to guess what our null hypothesis should be? P equals 0.75. Now, eventually, down the road, we're going to learn how to write hypotheses for several different kinds of parameters, okay? Remember how sometimes we might use X bar to make estimates about mu? So what I don't want you guys to do is write that do you know what some people sometimes put for their null hypothesis? They put the 0.75. That doesn't communicate a lot, okay? You want to put P is equal to 0.75. All right. Now, what's P stand for? It's going to be the true proportion of time that Lombo beats Richards. All right, and so we've written our null hypothesis. Our alternative is what we want to show at the end. So the big key here is this convincing evidence that she is overstating her ability? So what are we trying to show? She's less successful than 75% of the time, right? So P is less than 0.75. Okay? So guys, as we look at what we have so far, what procedure would be appropriate to test these hypotheses? That's kind of how we think this through. So I asked myself, what procedure is this? The name of this procedure will be a one sample Z test for P. And we don't have to define P, we've already done so. And the last thing we need to do is say, am I allowed to do, these particular settings, am I allowed to run this test? So we say, I don't know, let's check our conditions. Let's start with the random condition. Oh, perfect. We were given that this is a random sample. Normal. So we would do 100 times 0.75 and 100 times 0.25. Because I'm pretty sure that works out to be 75 and 25. I'm not very good with percentages, but when the sample size is 100, I can handle it. That works, okay? Lastly, independent. Since our random sample was of the crossword puzzles, I'm very comfortable saying that 100 is less than 10% of crossword puzzles. Because I know I have done at least 1,000 crossword puzzles in my lifetime. Cool? How do you guys feel about setting up the test? Does this feel familiar enough that really adding the hypotheses is the only new piece to it? Okay. Next. What kind of calculations do I expect out of you guys? Well, I'm gonna always ask you to write down 2 different calculations for a test of hypotheses. Okay. The first of which is going to be your standardized test statistic. Now, you guys see that there is a formula right there that says standardized test statistic, and it says statistic minus parameter over standard error. Everybody see that? Okay. In this setting, what is my statistic? It is p hat. What's my parameter? What's my value for p? P null, okay? And for your standard error, you use a value for P. If you have one, which we do, it's going to be P null, okay? So we're going to do P null, 1 minus P null, all over it. Now, I'm going to go back to Joy one more time. Can Joy smell Parkinson's? Probably not one more time, guys. I'm probably going to keep coming back to Joy because it's a good anchor test. Can she smell Parkinson's? Yes. And what was it that convinced you? What convinced us? That's what convinced you? Like, you guys, I'm going to point this out. You were convinced at 11 out of 12 before you were convinced at 12 out of 12, yes? Was everybody convinced at 11 out of 12 before we even knew that that one she got wrong, she actually got right? Do you guys see what I'm saying? Okay, so why did the 11 out of 12 convince you?
Because it was so unlikely for the null, or for the null.
It was, so our p-value is a probability because it comes down to likeliness, okay? It is the probability of getting a sample, I'm going to put in parentheses, or more extreme, if the null hypothesis is true. All right. So the first thing I want us to do, guys, is for this example, let's go ahead and for the crosswords, let's go ahead and calculate that z-score, okay? So, in this setting, guys, what was p hat? What is the actual observed sample that occurred? 0.67. It was 67 out of 100, yeah? All right, so my z statistic will be 0.67 minus my parameter would be whatever I'm hypothesizing about p, which is 0.75, the p from the null hypothesis. And then I'm going to divide by 0.75, 0.25 over 100. This is where I'll let you guys figure out what is that standardized z statistic. What are we getting?
Is it negative?
It is negative.
Negative 1.848.
Cool. I'm going to call it negative 1.85, but yeah, cool beans. And why is it negative? Because our p hat is smaller than the, and pretty much anytime my alternative is a less than, my sample suggests less than, is probably, your z-score is probably going to be negative. Okay? All right. So the next thing we want to, so what does this really mean? This means that our observed sample is 1.85 standard deviations below what we would expect if the null hypothesis is true. Because remember, z-score is number of standard deviations. Okay? So is that a lot? Or we want to know, is it unlikely that this could have happened? I don't know. You know what I do know? That z-scores have a mean of 0, a standard deviation of 1. And we already said that the sampling distribution was normal because we checked that, yeah? And so really, if I want to know how weird it is, I could just find the area to the left of negative 1.85 on the z distribution. And that value, that probability, this is your p-value, whatever that area is. But I need some help with that because I'm not smart. What are we getting? I would imagine it is somewhere between 5% and 2.5%.
I have three short. 2%.
0.032? Cool. That sounds about right.
Can you just confirm with this table which one you press in the calculator again?
Inverse norm? Or no, I'm sorry, normal CDF.
Okay. Perfect. Thank you.
All right. Now, let's go back and kind of think through what this really meant. Okay? This is essentially a probability. Okay? So the first thing is, guys, at some point, you're going to get an extremely low p-value. It's going to say something like 3.7 e to the negative fifth. You know what kids do that gets them in big trouble? They say 3.7. What do we know about our p-value if it is a probability? It has to be smaller than 1. Is everybody okay with this idea? Okay, one other thing. Your p-value, if you, for instance, put 3.7, you get 0 credit for the calculation even if you have the correct z-score. Because what you're communicating is that you don't know what a p-value really is. It's an automatic deduction in grade. So if you have if you put 3.7, you go from a E to a P because you have the wrong number. And then you go from a P to an I because you gave a probability answer that's greater than 1. Yeah.
What if you put like 1.37 times 10?
That's fine. That's fine, because then you're showing you know it's a know how small it is. It's absolutely fine if you keep it in the scientific notation. But as you go through, just like we learned about a calculator shortcut for intervals, eventually I'm going to teach you the calculator shortcut for tests. And one of the things I need you guys to recognize is that it gets really, like right now, if you got a value smaller, like a 3.2 as your answer here, on the normal curve, you would be like, something isn't right because it's this tiny, tiny area. When you get to that shortcut, you can get that P is equal to 3.2 and not see it. Because you get so like ingrained in the plug and chug in the calculator gave you the value. That's why I'm pointing it out. Okay? All right, now, you guys, if I had to interpret what that 0.032 really means, okay, I might say, if Mrs. Turner can actually beat Mr. Richards 75% of the time. The probability we could observe a sample where she beats him 67% of the time or less. Where she,
The probability of recursions.
now, which one actually occurred? The 75% or the 67%? The 67%, right? And we're questioning the 75%. Would you guys say it's unlikely for her to only beat him 67% of the time? Yeah, it's pretty unlikely. 3%. Okay? Are you guys with me? Okay. So, what conclusion can we make? She's probably overstating her abilities. Because it's super unlikely. That I didn't mean to turn the page. Though, frankly, guys, if I had to pick which one of the two of them would overstate their abilities, it's not Turner. If I had to pick who in the math department would overstate their abilities, definitely me. Definitely. Everybody good? All right. So the basic logic of our conclusions goes, two different things could happen. If my p-value is small, like, I don't know, as small as 3%, or with joy it was like less than 1%, right? If my p-value is small, that's what actually happened, and it shouldn't. That means what actually should happen should not have been able to happen when the null hypothesis is true. So guess what we get to do? Reject the null. And if I rejected the null, I have my two competing hypotheses. I've rejected one of them. What can I say? The other one is true. Okay? If on the flip side, my p-value is not small, and honestly, that's what I would, instead of saying large, I might even say not small. Because when I say p-value being large, or a probability being large, kids tend to think of like more than 50%. Does that make sense? All right. So if our p-value is not small, then we can't reject the null hypothesis. So let's give an example real quick in this context. What if instead of 67 out of 100, she beat Mr. Richards 72 out of 100? So that her p-hat, that observed sample, was 72% of the time. You guys, if this was 72%, does that suggest that the alternative hypothesis is true? Yeah. But are you convinced? Are you guys convinced to say, nope, she beats him less than 75% of the time if in that sample you got 72 out of 100? It's pretty close, right? Could that 72% have happened by chance? All right. So from there, we could say, like, I'm not going to reject the null and conclude the alternative. But should I conclude that her success rate is 75%? No. I should just not conclude that it's less than 75%. Okay. So if our p-value is not small, we don't reject the null hypothesis. If I don't reject the null, how many hypotheses do I have that could be true? I have my null and the alternative. So guess what? Am I allowed to conclude anything? No. Okay. So we never conclude the null. We either reject the null and conclude the alternative, or don't reject the null, and then we don't conclude the alternative. Do you guys see that there's a difference between not concluding something versus saying it's true? Okay. All right. Now, hold on. So, if I say your p-value has to be small or not small, how small does it need to be?
Less than 10%. Less than 5%.
Less than 1%.
You guys are absolutely hilarious. Let me tell you why. We said we had a 10%, a 5%, and a 1%, yes? Okay. How small does your p-value need to be? The answer to that is it depends on the context. We'll go into a ton of detail about how you make this decision on Tuesday. Okay? There are different levels of significance. The symbol we use to describe the level of significance is the Greek letter alpha. Okay? And there are 3 commonly used values for how significant our sample needs to be. They are 0.10, 0.05, and 0.01. This is why I find you people hilarious. Now, Are you guys good guessers, or can we understand that alpha equals 0.10 is not that different than a 90% confidence interval versus a 95% confidence interval versus a 99% confidence interval? There's a relationship there that maybe is like brewing in your guys' subconscious, or you're really good guessers, one of the two.
It was not brewing in mine at least. Didn't
I just was kind of taking what we did in the problem 4 because it was 3%, and that's why.
How we feeling? So this is the groundwork. You guys will have a quiz on this on Monday.